Hello, welcome to Special Topics 2 Integrated Presentation and Data Analytics course. This week, we're going to undertake data analytics, and if I'm not mistaken, we are on the last module of our data analytics course. Specifically, the predictive analytics. In this session, we will also include prescriptive analytics because some of the techniques that will be demonstrated later is categorized under prescriptive analytics. Let us just flash again the data analytics framework. This has been expounded many times. We're only going to focus on the last procedure, which is on the analytics portion. We have three categories: descriptive, predictive, and prescriptive. We're done with descriptive analytics, which is the basics of analytics that can be produced from our datasets. Basically, it's just the descriptive statistics. The higher level of analytics that can be done are predictive and prescriptive analytics. Predictive analytics seeks to find patterns and trends within historical data to provide useful information that can aid decision makers. Predictive analytics asks the question, why did it happen? The difference with descriptive analytics is that descriptive analytics asks the question, what happened? In predictive, why did it happen? Prescriptive analytics seeks to find the best solutions given the set of assumptions and available data. Prescriptive analytics asks the question, what should be done next? The main difference between prescriptive and predictive analytics is that prescriptive analytics gives us the best solution, while predictive analytics just gives us the different options. An example field that greatly uses predictive and prescriptive analytics is machine learning. A concrete example is the YouTube recommendations product. When we try to watch a video that we have searched in YouTube, you can see that at the bottom of the video there are recommendations. So based from our data points from searches and the vast data points available in YouTube, the YouTube algorithm predicts videos that we want to watch so that we will not leave YouTube. Here are the list of different techniques that we will try to understand and demonstrate later. First, we have scenario analysis. This is under predictive analytics. We also have linear programming, which is a mathematical method under optimization. And optimization is a prescriptive analytics technique. We also have classification under predictive analytics. We have a familiar ANOVA, which is a statistical technique. Analysis of variance is under predictive analytics. We also have regression, another predictive analytics. And lastly, we have time series decomposition, which falls under predictive analytics. Scenario analysis. Analyzing future events by considering alternative possible outcomes. In Microsoft Excel, scenario analysis is more commonly termed as what-if analysis. Optimization, finding the best solution based on a system of constraints and objective function. Max, min, target. Optimization is a higher level scenario analysis. So one of the methods used is the linear programming. Just like the differentiation of predictive and prescriptive analytics, the difference between scenario analysis and optimization is that scenario analysis gives us different options, but for optimization, it gives us the best solution. Classification, predicting values based on historical training data. One example of classification is the Facebook profile product. When we try to set up our profile in Facebook, there are optional fields that we need not to fill out. But once we try to view our profile, we're surprised that some of those optional fields have now data. That is because Facebook analyzes our data points based from our searches, based from its vast data points collected, and it's up to us to check whether the suggested content is appropriate. Analysis of variance, a statistical technique to analyze whether mean differences are significant. ANOVA basically is just a comparison of means, which tells us the statistical significance. We will be reminded of hypothesis. So it can be translated into mu is not equal to 0, wherein mu is symbol for mean. Regression, analyzing the relationship between a dependent variable given a set of independent or explanatory variable. The main goal of this regression is to generate a trend line to predict future values. We can treat our learning here in data analytics course as a stepping stone or groundwork for future courses, like machine learning. I myself is learning machine learning now, and one of the techniques used in machine learning is regression. They use different terminologies, but the semantics are the same. Regression here in data analytics, we talk about dependent variable and independent variable. While on machine learning, we use the terms labels and features. So labels is equivalent to dependent variable and features is equivalent to independent variable. Let me just show you a scatter plot. This scatter plot, the diamonds are the data points, and then the blue line is the linear regression. So this blue line in machine learning is the model. Based on the different data points available, we're trying to create a line function that will later on be our model to predict future values. The more data points that we train our model, the more accurate the model to predict future values. Lastly, we have time series decomposition. Predict the future values based solely on the past values with respect to its trends and seasonality. The difference of time series decomposition with what we have learned last week with moving average is that time series decomposition has a time element. Decomposition here means that we separate the trend and seasonality component, make calculations, and then return them back so that the result can be useful in predicting future values. Now, the difference of time series decomposition with regression is that time series decomposition only needs the time and seasonality component, while for regression, we need variables. We will try to demonstrate predictive analytics and some of the prescriptive analytics, again using Microsoft Excel. Now, just like what I've said a while ago, understanding regression could be a groundwork for us to understand later on regression in machine learning. We're going to demonstrate predictive and prescriptive analytics using cases, and it's up to you to analyze and make these demonstrations as analogy in understanding your own datasets and using the different techniques. First, predictive analytics technique that we're going to demonstrate is scenario analysis. Let's first read the case. Lighthouse Cooperative sold 20 million worth of Chicharabao, Miscara, and Chicharica. The cooperative incurred 80% of sales as their production costs. In operating the cooperative, fixed costs are 1.5 million. So we transform this case into its dataset form. This is how it looks. We have a table that have items, sales, variable cost ratio, cost of goods sold, operating profit, fixed costs, net income. These items have two field types, manual and calculated. Manual input field types are sales, variable cost ratio, fixed costs, and calculated field types are cost of goods sold, operating profit, and net income. So we say calculated if the value is in formula form. So we say it's manual input field type if we can manually input the values. So don't be afraid of the formulas. Just refer to the financial statement formula on the right side of the screen. So we have questions. Number 1, assuming all other factors are constant, how much sales do Lighthouse Cooperative need to get 4.7 million net profit? The best technique that we are going to use here is scenario analysis. Go to Data ribbon, under Forecast, click What If Analysis, and go to Goal Seek. So Goal Seek can be used by using a single variable to predict values. So for question number 1, we want to set cell net profit to value. Based on the question, it's 4.7 million by changing how much sales. So the sales value field. Then just click OK. GoalSeek automatically calculated the scenario. So we need 31 million sales for us to get a net income of 4,700,000. Question number 2. With 31 million sales and 1.5 million fixed costs, what variable cost ratio should Lighthouse Cooperative aim to get 5.3 million in net profit? So the question, again, uses a single variable to predict a future value. The technique to be used here again is scenario analysis goal seek. So let's go to Data ribbon, Forecast, What If Analysis, goal seek. Set cell again to the net income and to value. Based on the question, it's 5.3 million. By changing cell, what variable cost ratio? So it's the cost ratio that we will select. Press OK, and it automatically calculates the scenario wherein we need 78% variable cost ratio for us to have a 5.3 million net income. For question number 3, with 31 million and variable cost ratio at 78%, what fixed costs should Lighthouse Cooperative aim to get 5,999,999 in net profit? So just like number 1 and 2, we again use scenario analysis goal-seek to answer this question. Lastly, for number 4, what is the break-even point in terms of sales with 78% variable cost ratio and 800,000 one fixed cost? So for us to do this, let's just change fixed costs here to 800,000 one. Go to data ribbon, forecast, what if analysis, goal-seek. Set cell to net income again. And the meaning of break-even point is that net income should be 0. And by changing cell sales, let's try to click OK. And it automatically calculated that the sales should be 3,647,063.38 for us to have a break-even point or 0 net income. Goal-seek is useful when we are confronted with a single variable to forecast a value. But what if we need 2 variables to move our forecast? Then goal-seek will not be of use for us. There is another variation of scenario analysis that can help us when we have 2 variables to move our forecast, and that is data table. Let's read again the case. Lighthouse Cooperative is creating a simple financial statement computation to evaluate profitability scenarios. The cooperative sold 20 million sales of Chicharabao, Miscara, and Chicharica. The operating margin is 10% and cost-income ratio is 50%. Again, we transpose this case into its dataset form, and we have items, sales, revenue, operating expense, net income, operating profit margin, cost-income ratio, and profit margin. Again, there are 2 field types, manual input and calculated, wherein manual input are sales, operating profit margin, and cost-income ratio, while the rest are of calculated. So I have questions here. What combinations of operating margin and cost-income ratio will result in highest profit margin? So we have 2 variables that we need to move, which are operating margin and cost-income ratio. Operating margin has values 10%, 20%, 30%, 40%, 50%. And cost-income ratio has 80%, 70%, 60%, 50%, 40%. So these are the different scenarios for these 2 variables. The first thing that we're going to do is we need to transpose the different values of the operating margin and the cost-income ratio into a table form. So let's try to copy this and put it here. And we need the cost-income ratio as our columns. So paste special transpose. And then in between, we need to reference the cell of the profit margin here. After that, we just need to highlight the table and go to data ribbon, what if analysis, data table. The raw input cell will be our cost income ratio, and then the column input cell will be our operating profit margin. Once all is set, just click OK. We just need to transform this into its percentage form, and there you have it. Different scenarios are provided for us. We can further visualize this by using an ETL technique that we have learned from our past learnings. Go to Home ribbon, Conditional Formatting, Color Scales, and this one, the first one. So this visualization is more commonly called as heat map. We have the red, yellow, and the green. It's like a stoplight. When the value is on the green, it is the highest value. So the answer to this question is that the combination of operating margin cost income ratio that will result in the highest profit margin is the combinations of 40 cost income ratio and 50 operating profit margin. If we don't need to weigh options or scenarios and we just need the best solution, then we don't need scenario analysis, code-seek, and data table to solve our problem. Instead, we can use linear programming, and just like what we have discussed in our lecture, linear programming is an optimization method, which is also a prescriptive analytics technique. The first thing we need to do is to go to File ribbon, Options, Add-ins, Excel add-ins, and go. We need to enable a plugin called Solver Add-in. So this Solver add-in is available on all versions of Microsoft Excel, either in Mac version or in Windows version. We just click on Solver add-in and press OK. To know whether the Solver add-in is already enabled, go to Data ribbon. At the very end of the options Analyze, there should be Solver at the bottom of Data Analysis. So let's demonstrate using this case. 3 vegetable farms owned by Kim Chu with processing capabilities are available for monthly production of kimchi. The capacities of the 3 farms are 46,000, 23,000, and 60,000 packs. The number of packs required for kimchi cabbage, radish, cucumber, and mustasa are 28,000, 65,000, 35,000, and 70,000 respectively. The profits in pesos per packs at each plant for each kimchi veggie are shown in the table below. We have rows for the farm and we have columns for the different kimchi vegetables. As you can see, we have positive net profits and we also have negative net profits, especially on cucumber. Here are the questions. Number 1. How many packs of each kimchi veggie should be produced in each plant so that total profit is equal to 30 million? So let's transpose this case into its dataset form. Let me just unhide this. So as you can see, we have an almost blank dataset as compared to our data sets from scenario analysis a while ago. So let's just run through it. We have production and profit data sets. We have blank values for production of each farms on different kimchi vegetables. But at the very end of each farm and kimchi vegetable, we have a formula. So the formula is the sum for each of the farms and the sum for each of the kimchi vegetables. As to the profit dataset, we also have uh, initially blank data, but we have a formula here at the end of each farm. So it's sum product for profit and production. And for the total profit, we have the sum of those sum product of farms 1 to 3. Let's transpose data from our case. We need the net profit data to be transposed. So let's just copy it and just paste values. And we need not to transpose the data for the capacities for our 3 farms and the number of packs per kimchi vegetable, because that is what we're going to predict. But what we know is that the data that were provided in this case is that the sum per farm and sum per kimchi vegetable should be equal to the values specified on the case. So going back to question number 1, how many packs of kimchi veggie should be produced in each plant so that total profit is equal to 30 million? Let's go to data ribbon, analyze solver. We have to set the solver parameters based on our case. As to question number 1, our objective is to check the total profit. So we need to reference set objective to the total profit, and then based on the question, it should be equal to 30 million. So we choose value of 30 million. By changing variable cells, though kimchi vegetables per farm, all of this from cell C3 to cell F5. And then we need to set the different constraints or assumptions that are available on our case. So those are the data that we did not put on our data sets, which are the capacities of the 3 farms and the number of packs of each kimchi veggie. So we will put those constraints or assumptions one by one. Let's just click add. Cell reference. Let's start with the capacities of the 3 farms. So we need to reference this. Lesser or equal to 46,000 based on the case. Add. And then farm 2 total production lesser or equal to 93,000. Add. And then farm 3 lesser or equal to 60,000 packs. And then add. And we also need to add constraints for the number of packs per vegetable. So we need to reference the total production for cabbage. This should be equal to 28,000. Add. Cell reference the total production for radish equal to 65,000. Add. And then reference total production for cucumber equal to 35,000. add. And lastly, reference the total production of mustasa equal to 70,000. Click OK. Once you click OK, we can see different constraints that we've added to the list. Once everything is set, click Solve. And Solver automatically calculated the result. Let's just transform this into a readable form. However, as you can see on the results, we have floating point values. And in reality, there are no number of packs that is a floating point value. So let's return to our solver to add a constraint to eliminate that kind of error. So let's click add, and then we want all of these cells to not be floating point but an integer. And if we click add and click solve, then we fix the error and recalculated the best result. Question number 2. How many packs of each kimchi veggie should be produced in each plant so that total profit is maximized? Now, to answer this question, let's go back to data ribbon, analyze, solver, and instead of setting the, the objective to value of 30 million, we just set it to max and just solve it again. As okay. As you can see, total profit is maximized when some of the farms will have no production on some of the kimchi vegetables. As you as you can analyze on the tables, those without values here have low or negative profit from the table here. So like for example, on cucumber, those that have negative net profit has no uh, values in the production so that we could maximize our profit. Last question. Max profit if each farm were required to produce at least 500 of each kimchi veggie packs. Let's go to data ribbon, analyze solver, and then we just need to add another constraint, add, and we reference all of this from C3 to F5 and change this to at least. The question is at least, so greater or equal to 500. And then click OK. And then click Solve. But there we have it. It's optimized, and the resulting profit is 34,970,000. Another optimization demonstration is with the use of distance formula. Distance formula is also called dispersion statistics, wherein these are just the computation of the variances and standard deviation. So we have a case here, a case for warehouse. And as we can see on the left side is the data sets for warehouse and branch. And the data for these data sets are location data. So you will be those who have undergone special topics GIS is familiar with latitude and longitude. And these data sets are visualized on the center using a scatter plot, wherein The x and y axis are our latitude and longitude values, and the points are the warehouse and the branches. QGIS offers better computation and visualization than what we're going to do here. But for the purpose of this course, we're going to use Microsoft Excel. So we have questions here. We want to identify which single warehouse is best for Minigo branch, and number 2, which single warehouse is best for 610 branch, and number 3, which warehouses are best for each specific branch. The goal of each of the questions is to identify the shortest path. That is why the best solution is to use distance formula. Let me just unhide some cells. And as we can see, beside the branch dataset is a cross-tabulation of the warehouse dataset. So we have columns for uh, all of the 3 warehouses. And we examine the formulas. As you can see, in this cell, we have a formula of square root of, uh, example here is B9, which is the latitude for Minigo branch, minus B3, the latitude for warehouse 1, raised to 2, plus the longitude of Minigo branch, minus the longitude of warehouse 1 raised to 2. These are familiar formulas. As you can see, within the square root formula are variance formulas. So since we have 2 related fields that we're going to calculate, we need to add those 2 before we square root it. And the square root here is the standard deviation formula. So we apply the distance formulas on all of the cells to calculate the distance output on each branch for each warehouse. And then we have at the bottom, to answer question number 3, we just need to consolidate all of the distance output for the Minigo branch, example in warehouse 1, and apply that formula to all of the other warehouses. Same is true with 610 branch. Just need to average all of the distance output and apply the formula on other warehouses. So the best warehouse for Minigo branch is warehouse number 3. So as you can see here on the scattered plot, warehouse number 3 is located here. Its average is almost comparable with the average for warehouse 2. And as you can see here, as you might notice, there are Minigo branches that are near warehouse 2, but there is an outlier branch that is near warehouse number 3. The best warehouse for Minigo branch still goes to warehouse number 3 because this outlier made the difference. Now to answer questions number 1 and 2, you just also need to determine the lowest of the values. For example, on 610 branch, warehouse 2 is the best single warehouse. Another predictive analytics technique that utilizes distance formula is classification. Let's examine this vital statistics case. Here we have 2 datasets. One is training data and the other one is new data. As you can see, on the training data, we have a complete data set. However, for the new data, it is incomplete because the gender is unknown. So what we would want here is for us to predict the classification of the gender variable on the new data with the training data that we have. So how do we do it? We use the classification using distance formulas. Let's unhide this. So just like what we have done with optimization with the warehouse case, we would apply the distance formulas on all of the uh, customers on the new data by cross-tabulating it with the training data, with all of the customers on the training data. Let's examine a cell with the formula. As you might notice, we have three variances formulas because we have three variables that we are dealing with, which is height, weight, and foot size. Just apply those to all of the cells so that we have the distance output per training data customer. And as you can see, we have to group the distance output by the gender for us to easily calculate the final value that will be used for the prediction. So we have a group male customers here and we have group female customers here. There are two ways for us to predict the gender for the new data customers, and one is using average prediction. So what we want here is we just want to average all of the distance output for male and all of the distance output for female and apply those formulas to all of the cells until customer C16. And the prediction formula is if P15 average male distance output is lesser than Q15, the average distance output for female, true value is male and false value is female. So that's the formula for prediction. Apply those until customer C16. So we have now a prediction that customer 9 is female, customer 10 is male, and so forth and so on. Another way is, let's unhide this, using the minimum prediction. So instead of using average formula, we use minimum. We just want to have the minimum of all of the four distance outputs, including here on the female, and have those values until customer C16. And the formula for prediction is the same. If minimum distance output for male is lesser than minimum distance output for female, true value is male and false value is female. As you can see, the outcome is the same prediction. Another predictive analytics technique is ANOVA, or analysis of variance. Again, analysis of variance is just a comparison of means, and it is more of a statistical technique. So let's examine this case for ANOVA, which is a rice production case. Let me read. A special program was implemented in Nueva Vizcaya for increasing rice production. The question is, are there significant difference when compared to Cagayan and Isabela? So the goal of this is to determine if the special program has impact on the rice production of Nueva Vizcaya by examining the differences with Cagayan and Isabela. We have two datasets here, the upper part and the lower part. So the upper part is a data set, we have 1, 2, 3, 4, 5, 6, 7 rows each. These are sampled from a population, and the 10th row is just the sum of the production of all of the sampled population. Same is true with Cagayan and Isabela. As you can see, if you might try to analyze the sum of the values for each of the three provinces are near, which you might conclude that there is no significance in the comparison of their values. On the bottom part, we have here another data set, and let's hypothetically say that this is the data set wherein the special program for Nueva Vizcaya is implemented. And as you might notice, the values are distant. So you might conclude also that there is significant differences on the values. But how do we prove it? The answer is using analysis of variance. So I have here the results of the analysis of variance on each of the data set. The left part is the result for the top data set a while ago, and the right side is the result of the bottom part of the data set a while ago. Let's examine each of the scatter plots first. So visually, as you can see, the values for the Nueva Vizcaya as compared to the values of Cagayan and Isabela seems to have no difference because they are on the same level. But on the right side, on the second scatter plot, as you can see, the values for Nueva Vizcaya is quite different, or is really different with the values of Cagayan and Isabela. So visually you can say that there is really significant difference. There are two things to check on the result of the calculations for analysis of variance. The first thing is the comparison of F and F critical. And the second thing is the value for p-value. So the first thing is you want that F should be greater than F critical. And for the second thing, we want p-value should be lesser than 0.05. If those conditions are met, then we can conclude that there is significant differences. In this case, F is lesser than F critical. So condition 1 is not satisfied. And then p-value is 0.76. Condition 2 is also not met. So statistically, there is no significance on the values for dataset 1. As for dataset 2, F is greater than F critical. So condition 1 is met. And p-value here is 0, which is far lesser than the 0.05. So, statistically, there is significant differences on the values. How do we do analysis of variance? It's simple. Go to Data ribbon, Data Analysis, and look for Analysis of Variance or ANOVA, Single Factor. In this case, we're going to use ANOVA Single Factor because we're only analyzing a single classification, which is province. But if we want to analyze two classifications, we can use the other variations or models that Microsoft Excel Data Analysis Toolpack can offer. So just click ANOVA Single Factor, and we want our input range is just the values of the sampled population. And as you might notice, alpha 0.05, this is the margin of error, remember, in your statistics. And the output range, I want to put it here. Just click OK, and there it is. A very useful predictive analytics technique, as was pointed out during the lecture, is regression analysis. The ultimate goal of regression is to generate a trend line, wherein that trend line is the model to predict future values. In this demonstration, we're going to use the algebraic equation for the linear regression for our model. And that is y is equal to alpha plus beta x, wherein y is our independent variable, alpha is our constant for the intercept coefficient, and beta is another constant for our independent variable coefficient, and x is our independent variable. Let's examine the dataset for this case. So this case is again a rice production case. We have columns for municipality, production, fertilizer, seeds, and program. What we would want to do in this case is that we want to predict the values of production given a set of data for fertilizers, seed, and program. Well, let's transpose this dataset to our algebraic equation. We now know that y, or the dependent variable, is our production. We don't know alpha yet, and then plus, we know that our independent variables are fertilizer, seeds, and program. So we're going to have those three independent variables here. So beta times the value for fertilizer plus beta times the value for seeds plus beta times the value for program. So initially, this is our linear regression model. For us to compute for the value of our dependent variable production, we need to know the regression statistics. For us to do that, go to Data ribbon, under Analyze, Data Analysis, and just find Regression. Okay, and just click OK. Input Y range, we want the data for production. And for the input X range, we want the data for the different independent variables. And just click labels because we have labels for the variables. And output range, I want to put it here. Once all is set, click OK. And we have regression statistics. There are a few things that we want to check here on the regression statistics. The first one is the adjusted R-square. The second one is significance F. And then we want also to check the coefficients and p-values. Let's try to check adjusted R-square. So adjusted R-square here is 0.61 or 61%. This just means that the training data that we have, including the independent variables that we have, is 61% sufficient. So technically 61% is okay. What we're trying to say here is that the more data set that we have for training our linear regression model, the better the adjusted R-square. Not necessarily that we have more independent variables, because just like what we said a while ago, the dummy variable might affect the significance of the model. Next, significance F. What we want to check here is that if significance F is greater than 0.05, then our linear regression model is insignificant. We have to change everything. But usually, it's lesser. And then, we have the values for coefficient here. These are the values that we want for our linear regression equation. So for us, just to visualize it, production is equal to A here is provided here. So it's the intercept. So intercept value plus the beta now we know is 0.03. So let's just try to transpose it, times the value for fertilizer plus beta for seeds is 0.18 times seeds plus beta for program is 2.3 times program. So there we have it. This is the formula that we're going to use to predict future values for our rice production of non-existing municipalities. Let's try to have an example. If I want a 22nd municipality and I have the data for the fertilizer seeds and program, let's say 200 bags of fertilizer were given to that municipality, and 50, and program, special program was implemented. Let's try to put 1. Using the equation, intercept is this value plus this one times fertilizer plus this one times seeds plus this one times program. Enter. And there we have it. We predicted the value of 206. Further examine the validity of our linear regression model. Examine p-value. Again, if p-value is lesser than 0.05, it means that the independent variables are significant in our model. However, if it's greater, then the recommendation is to remove that independent variable. So just like in this example, the program is 0.67. It's far greater than 0.05 threshold. So we need to change program into a different variables to make our model more valid. Again, regression would be useful to your future learning undertakings, especially on machine learning. So I hope these demonstrations would be useful, and all of the other predictive analytics technique that was demonstrated would be useful to your current and future undertakings. Thank you and goodbye.